All right, so I told you guys last day that I'd covered most of the new material that I want to cover for this class in terms of small molecules and drug discovery. So today, what I want to do is kind of take what we've learned and put it to like real practical use. So last night I got online. I went to the Kaggle website, which is a fun website. If you guys haven't seen it, they have a lot of different like competition, like machine learning type competitions there in like every possible domain, and a number of them are in life sciences and this one, and so you can download models, you can download data sets, and this particular data set is a set of molecules with like a binary classifier on whether or not they cross the blood-brain barrier, right? And we talked the other day about blood-brain barrier. So that's going to depend a lot on the hydrophobicity and the size of the molecule. But let's see if we can build a model to get a little more precise than that and start to predict whether different molecules are going to cross the barrier. So we can go online and read about the data set. So it's got about 2,000 compounds, and they show you kind of a preview of the data set here. So you can see it's just a spreadsheet, right? And so it's got a numerical ID, it's got the name of the molecule if there is one. And then a number 1 or 0, depending on whether it does or does not cross the blood-brain barrier. And then the SMILE string, right? And we walked through like what the SMILE strings mean the other day. So the first thing we notice here is that there's about 483 zeros and 1,500 ones, right? So it's 75% 1. And so now we know if we're like later on, we're going to look at the accuracy of our classifier. We know that we can build a classifier that's like about 75% accurate by just having it spit out 1, right? So that's our baseline, right? 50% accurate is not our lower bound. It should be 75% accurate. And then we want improvements on that. So we want to see how far can we get from a dumb classifier that just says, oh yeah, everything goes across, to a smart classifier that, ideally would be like 100% predictive. Okay, so that's where we're starting. And I'd like to kind of walk through how we would build that model. I'm going to try to like build the model for you guys in real time, but I also like built it last night. So if we don't get through it, I'll scroll down to the right answer, but I want to go through it slowly so that you can kind of like see the logic here. Okay.
It's like in the cooking shows.
Like in the cooking show. Yeah, we're gonna French chef it, Actually, this model is going to be really, I thought about that, like, oh, we'll do like a little French chef where we'll start to like run the model, and it might take hours and hours, and I'll show you the answer. And it turns out we can actually build a very small model here. We can train it even without GPUs, and it'll kind of run in real time. Okay. So I'm just setting up, if you guys have used Google Colab, I'm just giving it access to my Google Drive. Can you guys see the text there, or should I?
Does everybody want to come closer, please? Just they think I'm on.
But can you guys read the text?
I mean, from here I can.
Okay.
And if I can, they can.
Oh, I know, right?
I know.
Let's see. See if I can increase the font size. Oh, zoom in. Yeah.
Definitely. That's good.
You think?
Yeah.
Okay. All right. So we're going to install a couple packages that are going to be useful. So we'll install RDKit and Kaggle, just so we can download this data set from Kaggle. We'll run that cell. Okay. And then this is just downloading the data set itself. Okay, so now we've got our data. Okay, so we have like a spreadsheet basically that has all of the smile strings, and it has this label 1 or 0 as to whether or not it crosses the blood-brain barrier. So what's the next thing I need to do? Like, what do I need to do to start building a model? I can't just put in smile strings. I'm going to need something else as the input to my model, right? Any ideas? Any suggestions? What we should use? We talked about a lot of different like representations of molecules. Like, what would you guys recommend? Yeah. It's definitely going to be a PyTorch tensor. But how are we going to get from a smile string to like a tensor of numbers? We've got lots of options, and they're kind of all valid. I picked one, but I'm curious to, let's see like the universe of options that we have to choose from. So what are the problems? What are the problems from going from a smile string to like a fixed length vector of numbers?
Model or turn it into a graph and use a GNN or something.
Yeah, so that would be a great choice, right? Because we talk a lot about GNNs, and they make a lot of sense. It really starts with the molecular graph, so it's got all the information on the molecule. The problem with the GNN, right, is like we've got a vector of numbers for every atom in the molecule, or like the paper we talked about last day, is a vector of numbers for every bond in the molecule. But what we want to train our model is we want a fixed length vector going in, right? So there's a lot of ways to do that. In the GNN lecture, we talked about, okay, how do we do graph-based classification? We can kind of add all those vectors together. We could add them and then divide by the number of atoms. We could connect them all to like a dummy node and parameterize that. So we have a lot of options, but that's basically the problem. How do we go from a list of inputs of variable length and go to a fixed length vector? So the solution that I came up with last night was, well, let's get online. Let's get online and see what people are doing, right? So this is another website that you guys should all check out and be familiar with. It's the Hugging Face website. And so this is like a really popular website where people share different transformer-based models. And there's a nice API. So if you find a model on Hugging Face, it's very simple to like download that model and start using it right out of the box. And you don't have to do a lot of coding on your own. So this model is called Chemberta. And so BERT is a language model. And this Chemberta has basically been trained on smile strings. Okay, so we're going to input a string, and then it's going to give us out one fixed length embedding from that input. Okay. And so if you guys are interested, you can look up Chemberta and find out more details on exactly how that embedding is made. I haven't actually looked at it very closely. I'm kind of familiar with BERT, but I don't know exactly what's going on, under the hood for this one. But I do know a lot of people use it, and it's it's one of the leading kind of transformer-based models. So, so I pulled that in here. Okay, so I'm importing the Transformers API, which has access to Hugging Face, and I just wrote a little function here to convert smile strings to embeddings from that transformer-based model. Okay, so we'll run that. And yeah.
What is it?
Yeah, good question. So how do you tokenize a smile string? How do we go from that string of characters to a string of tokens? In the past, you know, I've tried just well, you can do character by character, and that's probably not going to be the best bang for your buck, because you know you'll have something like a C1 character and then a few other carbons and then another C1 where the ring gets closed. And so C1 is kind of an entity in and of itself, as opposed to treating it as C and then 1. Obviously, you can do everything on the character-based level, but then you need a lot more data because the model has to learn, you know, like what the appropriate chunks are. So I've tried various different things, kind of like ad hoc, and yeah, they tend to work okay. In this case, and this is one of the nice things about using these models on Hugging Face, is that like once I pulled in that model from Hugging Face for that transformer, it comes with a tokenizer that the people who built the model like thought was like pretty reasonable. And so I'm just using their tokenizer, and I don't actually have to know how it's chunking those things. Okay. And the next thing we're going to do when we define a model, and this part, you know, I want you guys to kind of pay attention to. I'm not going to try to like write it out like in detail, but it always pays to make a data set class. Okay, and data set will subclass, you know, whatever you make it, it'll subclass the, you know, the data set, you know, the parent data set class. And this class basically only has to have like 3 different functions. So it has an init function, and here in my init function, I'm going to read in this file that I've downloaded from Kaggle. Okay, I'm going to make a list of all the smile strings. I'm going to make a list of all the labels. I'm going to ignore the other columns. I don't really need them. And then I'm going to make a list of embeddings. So I'm going to call that function smiles to embeddings. That's using the Kemberta model, and I'm going to convert that list of smile strings to a list of embeddings. And now this dataset class is just going to serve up, you know, one embedding and then the label, which is 1 or 0, whether across the blood-brain barrier. Okay, so that all happens in the init function when I instantiate this dataset class. The other methods that need to be defined are a length function. So if we ask for the length of the data set, here it's just going to return the length of the list of embeddings. All three lists are the same size, so we could just return any of those lengths. And then it has to have a get item class, and get item is going to take one parameter, the index, and then it's just going to serve up the embedding and the label, right? So like the example and the label that we want to train on. Okay, so that's all that does. So since we have these things in lists anyway, we're just gonna pull that item, that index, out of the list, and then we'll return both of them. Okay. Okay, so that's our dataset class. The next thing that I encourage you guys to always do is define a data loader, and the data loader operates on the dataset class, and it just makes things really easy. So here I'm going to separate out my training set from my test set. Okay, and what I've done here is I've said Well, I'm going to take the length of the data set times 80%, and that's going to be my training size. And then the remaining, the other 20%, that's going to be the size of my test set. And then I'm just going to call this function random split with my data set, and then the size of my training set, a test set, and that's gonna return this split here with my training data set and my test data set, and then I'll make a data loader for the training data set, and I'll make a data loader for the test data set. Okay, and in the data loader, I'm going to specify a few different things. Okay, so in the training loader, the first thing that I'm going to specify, apart from the data set, is the batch size. Okay, and this is really important. In general, we're going to choose we kind of keep an eye on the memory that we're using, because we're often running on a GPU, and we're going to get the best efficiency if we can fill up most of the memory on that GPU with a batch. And so depending on how big the data is that's going in, we may be able to use a very large batch size, or we might have to use a smaller batch size. Okay. The advantage of using a large batch size, in addition to the speed up, is that when we compute the gradient, we're always computing the gradient on the batch of inputs that we're looking at. But ideally, we kind of want to be computing the gradient on the entire data set when we're updating the parameters, right? So the more of the data set we can look at any given time, the more accurate of a gradient we can get, and the more accurate the gradient, potentially the fewer steps of optimization that we need to go through. Yeah. And when I'm training the data, so I'm going to train it. I'm going to pass through all the data once. That'll be my first epoch of training. And when I pass through the data again, I probably don't want to go in the same order. I want to kind of mix things up, because it could be that there's one parameter in the model that gets trained on a few examples, and maybe all of those examples are crammed into one batch. And so as soon as that parameter gets updated, it sort of forgets it, because those examples aren't in the other batches. And so I just kind of want to smooth things out and prevent it from getting stuck in a rut. So I'm going to shuffle the examples every time I instantiate or every time I call this data loader. And then with my test data loader, well, I'm probably going to use the same batch size, but in this example, I'm not going to shuffle them, because I want to compare the test from run to run, and maybe I'm not going through the entire set of examples. So I just want it to be really consistent. This is going to be my test. It's not involved in the training at all. Okay. All right. So once I run this, it's going to instantiate that dataset class, and it's going to start converting those smile strings to the embeddings from my transformer. Yeah. Do you have a question? Oh, shoot. Oh. Ooh. Oh, good point. Uh-oh. All right. Yeah, so that was a bug in my code. And now we're gonna see, because when I ran this last night, I got to 100% accuracy. And now we're gonna see for real how well it does or doesn't work. All right. That was not intentional. I'm glad you guys are paying attention. All right. So that's going to run for a couple of minutes. Ooh, it's so exciting now. And while that's happening, let's figure out what our model should be. Okay, so we're going to use torch. I'm just going to import a few things here. And so torch.nn, torch.neural nets is, that's where like most of the functions that that we're going to use are found. And we can define our model, okay? So one of the easiest ways to define models, and you can still define like pretty powerful models like this, is stop it. Through NN sequential, okay? And so here, I'm just gonna put different torch.nn layers in, and it's gonna take the output from the one, feed it into the next one, take the output from that, feed it into the next one, take the output from that, feed it into the next one. So I can define the whole thing as this, NN that's sequential, and then torch knows that's a model. If I want to, however, I can go through and I can take each of these layers and I can say like, x equals, nn dot linear, and then like x2 equals like another one of those on the output of x1, and like so on and so forth. So I can, I can define it kind of as an like an arbitrary Python function. And if I wanted to make like a variational autoencoder with those steps in the middle where I have to do like sampling or something like that, then that's how I would put that in. So it's a kind of a powerful framework. We're going to build a really simple model, so it's easy to just use this nn.sequential, and we're going to stack up different layers here. So the size of my latent vector coming from the embedding from the Camberta model is 768. Okay. So I've got a linear layer with 768 inputs. And then I want to downsize that. So let's go from that to like 128. And then I'll put another layer in here that takes 128, and let's downsize it again. We'll say 64. And then let's put in maybe one more layer where we'll take 64 inputs. And in this case, we're just predicting one thing. So if we're doing something multi-class, like there were 10 different possible outputs, then we'd want to output 10 different logits. In this case, there's two different outputs, like 0 and 1. So like I could define it that way. But I'm just gonna like put it down to 1 and have a number between 0 and 1 that'll kind of predict, whether it goes through the barrier or not. Okay. And so if I want that number to be between 0 and 1, well, I can pass it through a sigmoid layer. Okay, and so each of these layers, and you can get on the Torch documentation, and you can see like what are the different layers that are in the torch.nn, and that's like a good list of pretty much everything you've seen in class, and some of the things we'll talk about today. Those layers are all there, and it'll tell you how to define them. So, if I'm doing a sigmoid, it's just like taking a number in and running it through a sigmoid function. So it's between 0 and 1. So I don't need any parameters there. For my linear layers, I just need to specify like how many nodes are going in and then how many nodes are coming out. And different layers, will have different mandatory and optional parameters that we have to specify. Okay. All right. So this is my neural net. I'm going from 768 to 128, or 768, 128, 64, and then down to 1. What have I forgotten? What's that? Yeah. So this is all just going to be linear, right? So I wouldn't even need 3 layers. I could just pre-multiply those layers together. So that's not going to do me any more good than if I just said it was a 768 to 1 layer. All right. So let's put a nonlinearity in here. Ooh, yeah, and Google already guesses that I want to put a ReLU in. I do, thank you. We'll put one after this. Okay, and then our last one is going into our sigmoid function, so we don't need a activation there either. Okay, so here's our model, and now let's run that. Hopefully that's syntactically valid. Okay. All right. So we have our data loader, our train loader here, and we have our model. Okay. So now we just need a loop to train this thing on. Okay. So each iteration through our data set, we're going to call an epoch. So let's say number of epochs equals 10. Okay, so we'll run through it 10 times. For epoch in 1 through 10. Here, it's suggesting that I do this, and it's always a good idea. So when you're training your model, you can say model.train, and then when you're evaluating your model, you say model.eval, and then if there's any bookkeeping that it needs to do in terms of whether to update the parameters and things like that, it'll kind of take care of that for you, which is very nice. Or updating the gradient, actually. And so for each epoch, I'm going to loop through all of the batches in my data loader. Okay, I'm going to say embeddings and labels in train loader. And my outputs, whoops, are going to be the output of my model embeddings. And my model, even if it's like outputting a scalar, it's gonna put an extra dimension on the end of it, so it's not really going to be a scalar. There's going to be another dimension there that's that only has one thing, and that's going to cause me some headaches. So I can get rid of that with this squeeze function. And that's just like a lot of the bookkeeping that we have to do in Torch to make sure that we're operating on the right dimensions of the tensors that we have. Okay, and then for my loss function, I'm going to use one of these built-in loss functions. Pretty much everything we ever need is already built into torch.neuralnet. And in this case, we'll use BCE loss of our outputs and labels. Okay. Oh, look at that. All right, it's auto-completed the next thing I want to do. Okay, so now we're looping through our data loader. We're computing the model output. And then we also have the labels, so we can compute our loss function. Okay. Now we need to back propagate that loss function. So for every parameter, we know how like a small increase in that parameter affects the loss, right? And we want to minimize the loss. So the first thing I need to do is if any of the parameters in my model have a gradient that's already stored from some previous operation. So for example, the second time I run through this loop, there's going to be a gradient stored in all those parameters from the first time I went through the loop. So I'm going to loop over, for P in model parameters, I'm going to just zero out the gradient. So p.grad equals 0 or equals none here. So that's good practice. Well, not good practice. It's absolutely required. But I can either do that before I calculate my gradient, or I can do it after I'm all done. It doesn't matter too much. And now I want to calculate my gradient. And the nice thing about working in Torch is whatever computations that have been done up to this point to calculate the loss, now I just call loss dot backwards, okay? And all the parameters that went into that calculation, that backwards function is going to back propagate it through, and for each of those parameters, it's going to store their gradient, like as part of that parameter, right? So it's going to store it like p dot grad. So it'll have p dot data, that's the value of that parameter, and then p dot grad is going to be the gradient that was calculated from my backward computation. Okay, so now every parameter in my model has some value, and it has a gradient with respect to our loss. So I'm just going to loop through all the parameters in my model, and I'm going to subtract some constant. Here it's 0.01 times the gradient, and I'm just going to subtract that from the data here. Okay. All right. Great. Now let's see. Let's keep track of all of our losses. So say loss list, and we'll initialize that to have nothing in it at this point. And then after we calculate the loss, let's just append the value of that loss to a list, okay? And then down here, when we're done, oh, lovely. We can say, we'll make a dummy variable temp, which is just the average loss in that list. So that's going to be the average loss over that whole epoch. And then we'll print the number of the epoch and then what the value of that loss is. And we'll see, hopefully, that our loss will start out quite large. And as we train, it'll get smaller and smaller, right? So should we give it a try? Ooh, it works. Nice. Okay, so we're training over 100 epochs here, and our loss started out at like 0.61. But as you can see, it's getting smaller and smaller. And because this model is pretty simple, like it worked pretty well. And I put in a fairly, so this parameter here, 0.01, is called the learning rate. And we just kept it constant, and it's constant for like every parameter. And so it's really kind of a vanilla model, and it tended to work pretty good. If we try to train like much larger and more complicated models, we might need to do more in terms of getting that to work efficiently. Okay. All right. So now let's move on and let's calculate. Let me just redefine my model here. So that'll erase what we've done before. And now I just want to train it with a few more additions so that we can make a plot of kind of what the loss looks like, and we can compute the Well, for some reason, the code I wrote last night is is now not working. And the one we did on the fly is working better. Okay, I'm not going to worry about fixing that right now. But maybe if we have time after the lecture, I'll come back. Sorry, that was like anticlimactic. I wonder, maybe if I just start again, like start again up here. Okay, we'll try that, and then we'll come back to it, because maybe maybe I overwrote something. In fact, why don't we just restart the whole thing? Okay, load it up. We will. Oh, yeah, I actually know what happened. All right. To do. I need to define a few variables. My criterion, so that's going to be my binary cross entropy loss, and I need to define my optimizer, and that's just to use some of the fancier features here. So we're going to train with an optimizer called Atom, or Atom W, actually, Atom with weight decay. Okay, so we'll do that. We'll let that run in the background. Okay, and so now I want to switch to talking about like how do we train these networks in general, and kind of what are the principles and pitfalls and things like that. So you saw the kind of the most bare bones way to like train parameters in my model. And that's really just a gradient descent. And so I take my parameter and I subtract the gradient of the parameter times some learning rate. Okay, if I'm doing that like in theory or in principle, I'm doing it on my entire data set, then I'm doing gradient descent. In practice, I'm always running in these mini batches, right? In this case, we're doing 32 at a time. And so I'm only calculating the gradient over those examples in the mini batch, and then I'm updating the parameters based on that calculation. So that's often referred to as stochastic gradient descent, because it's kind of random, right? We shuffled our data loader every time we went through. It's kind of random which examples are put together into the same batch. And so it's not really gonna be the same thing as a gradient descent. And in practice, that's really the batch size and everything is done for pragmatic reasons, and making the computation use the GPU more efficiently, things like that. But it also has this property of regularizing the optimization, and it makes it harder for the model to kind of memorize the answer to what's going on in the training set. Okay, and we'll talk more about different ways to regularize later. Okay, so if we want to get fancier than just subtracting some constant, the learning rate, times the gradient from our parameters, there's a number of ways to do that. One is a whole class of methods called momentum methods. And we'll talk about what that is. but it's kind of like how it sounds. Like once you start driving the parameter in this direction, you tend to keep driving it in that direction. And the advantage of that is if the surface that you're optimizing over is a little bumpy, well, you've got this momentum and it sort of like pushes through and sort of effectively smooths it out. And then we'll talk about adaptive learning rate methods. There's many of them. And the idea here is that, you know, at different points of the optimization, we may want to spend more or less. We want to put more or less attention onto specific parameters. Okay. And so those are our adaptive learning rate methods. And we may want to change the learning rate not only over parameters, but like over time as well. Okay, so how does momentum work? Momentum is pretty simple. Here's like the basic formula is if I want to calculate the momentum is what I'm going to use instead of the gradient. Okay, and it's basically going to be, it's kind of the gradient, but I'm also going to say like what was the gradient, or actually what was the momentum in the previous time step. And then I'm going to take some average between the gradient that I'm calculating based on the loss for this batch of examples, and like whichever direction I moved in the previous time step. So if the previous time step straight ahead like this, and then I look at these batches and it's saying, no, you want to move in this direction. Well, you know, if my momentum is 0.9, then I'm going to move, you know, in a direction that's mostly, you know, where I was going before with a slight correction. And if you know, if the momentum is 0.1, then it would be the opposite, right? I'd be moving in the direction of the gradient with like a slight correction based on the momentum. In general, it's you know, probably going to be more like 0.9. So I'm you know, moving in the generally in the same direction from time step to time step. But if I get a lot of corrections that are all pointing in the same direction, then you know, then I can change that. Okay, and actually this is like parameter by parameter, so it's not really this orthogonal thing. It's more like, you know, if my gradient was here and then in this batch it's going the other way, then I'd still kind of be going forward. Okay, so with this formula, every time I apply this parameter, this momentum term, I'm applying it again to all of those previous time steps, right? And so this term, even if it's like 0.9, you know, my gradient from 3 time steps ago is like 0.9 cubed. My gradient from 100 time steps ago is like 0.9 to the 100th power, so it's like basically 0. And so it's this, you know, what happens is at each time point, I have like an exponentially decaying influence from the previous time points, okay? So that's the whole idea behind momentum methods. And that's basically what a momentum is. Adagrad is an algorithm that basically identifies features that are used less frequently. And what it says is, you know, once you've done a lot of updates to a certain parameter, then you want to go slowly, because oftentimes we see the loss go like way down initially, and then you gotta you know, turn the learning rate down because you're getting close to where you want to be, and you don't want to move as far, and so you want to like slow down a little bit. And at the same time, when you get to a batch where you have examples in that batch that are really informative for part of for one of the parameters in your model. Okay, so maybe it's a certain molecule with a certain kind of ring structure, where in your 2000 examples you only see it like 20 times. So when you see like part of the model that is informative about that feature and you want to learn from it, then you really want to pay attention. Okay, so it keeps track of like how big have the updates been on this parameter. And it basically accumulates them by taking the squared value and then taking the square root. So it's like a root mean square, and then it's just dividing the size of the parameter update by the kind of how much that parameter has been updated already. Okay, so you'll start to optimize a lot of your parameters initially, and then as you keep training, you're going to really focus on the parameters that haven't been updated yet. Okay, so that's kind of the idea behind AdaGrad. The the problem with AdaGrad is that you can get to a point where like lots of your parameters they've already been updated a lot, and you might need to update them again because the rest of your parameters have moved. But now, like that denominator is so small that your learning rate like goes to close to zero, and it just takes forever to train. So that's a problem. RMS prop kind of builds on AdaGrad because it says, okay, well, instead of just adding up all of the previous gradients, so eventually like things are like approaching zero, let's use momentum on that, that accumulation term, so it kind of exponentially dies off. And then you're only ever looking at like a window of previous gradients. So like once you've updated enough, if you've stopped updating this parameter, then you will forget that you updated it a lot in the beginning, and it sort of takes care of that problem. Okay. So the method that kind of builds on that now is Atom. And so what Atom does on top of RMS prop, and then on top of like keeping track of that gradient, that accumulation of gradients, is it puts a momentum term on the gradient itself. So it's taking RMS prop and then saying, okay, what if we also put momentum on the gradient itself? And that ends up being pretty useful for a lot of practical problems. And so if we just look at the number of machine learning papers that use these different algorithms, you can see that like Atom has really taken off in terms of being a really effective way to train a lot of these nets. Okay, so let's walk through how we use these to fit like a simple model. So the data I'm showing you here, this is from a line, ax plus b, y equals ax plus b. You can figure out what a and b are probably by looking at it. I don't actually remember. I think it's 2x plus 1 or something. And I just generated points on that line, and then I added a random number, right? So I just made like noisy linear data, but like my model literally has two parameters, like plus a noise term. And we'll never fit the noise term. We kind of don't want to fit the noise term, but if I put like a gigantic neural net and train it on this, it's going to fit it. It's going to memorize all those data points, but it's not necessarily going to produce anything useful. Okay. So here's just a kind of an example of what I just said. On top is this is the model that I'm going to use to train it, right? So I've got my linear layers, I've got my nonlinearity, I've got another linear layer that's taking those 1,000 inputs and adding them up according to some weighting function, and then outputting a number, right? So that's the model I'm going to train. And below is my model of appropriate complexity, right? It would just be a linear layer with one input, one output. That model is going to have two parameters. It's going to have our y-intercept, or our bias term, and then it's going to have one weight, right? Which would be our slope. But let's say, a priori, we don't know what the internal structure of the model is. So we're going to fit it with a model that has way too many parameters and is way too powerful, and then see what happens, right? And generally, what's going to happen is if we have some loss function, and we look at our training data, the training loss is gonna drop precipitously at the beginning, and then it'll continue to drop, you know, as we go on. And the more we train it, like the lower it's going to go in general. And there can be bumps. If we hold out a test set or a validation set, and then we train on the training set, but then we evaluate on the loss of the validation set, what we're going to see is, well, probably the validation loss is going to go down initially with the training loss, and it's going to go down because, you know, we start with like random parameters, so it's pulling us generally in the right direction. But then at some point, as we start to, if we have a simple model and we start to memorize individual data points, it's going to make us perform worse on data points that we haven't seen. Okay. And in general, there's we have a trade-off between model complexity and different types of error, and we can break the error down into three different components. One is going to be the bias, okay, and that really is how, you know, if we were to look at an infinite number of examples, where would the model be converging on? Like, our model is probably not the true underlying model, and so it's gonna, you know, it's not the perfect model, so it's going to converge on some point that is potentially not the right answer, right? So here we can see, like, there's a target and like a bullseye, and the y-axis here, these are examples of models with high bias. Okay, so the ground truth is here, and, you know, our model is predicting points here, or the ground truth is here, and our model is predicting points over here. So we have a bias model. Down here, you know, as we sample an infinite number of points, we're like spot on, so our bias is very low. And here you can see the points are more spread out, but the more we sample, you know, the closer the average gets to the true answer, because the bias is low. So that's our bias term. There's also a variance term, and the variance is exactly what it sounds like. You know, these two examples, there's very little variance between what the model predicts for these different inputs. And over here on this side, we can see two models that have high variance. So this is high variance around a biased answer, and this is high variance around an unbiased answer, right? So these are kind of our two terms, and there's really there's a trade-off between these two, and then the last form of error is just irreducible error, and you can think of that as, well, gosh, if we're collecting data with some instrument that we're using to measure a physical process, and now we're going to try to, like, fit the you know, we're taking that as the ground truth, and then we're going to, like, build a model to predict the output of that instrument. Well, that instrument, it might be noisy in itself, right? Every physical measurement we take is going to have some error, and even if we have the best model in the world, it will never be able to, you know, predict, like, what is the error in our instrument, right? Okay, so we have this trade-off between bias and variance, and that's where regularization comes in. And so regularization is basically what we use, like, when we have these models that have way too many parameters, we can trade a little bit of bias. So we're not going to try to predict the exact answer. we're gonna put another constraint on the problem that is really intended to prevent overfitting. But by virtue of the fact that like the thing we're trying to optimize is not the right answer, like that inherently is going to put some bias into the process, right? So it's gonna take a model with very high complexity and reduce the effective complexity of that model because we're putting a constraint on it. And hopefully the goal is that that's going to help us generalize to new data, or like go from our training set to our test set. Okay, so what are some regularization techniques? Well, the first one is really simple. If we go back to this curve, we could just stop here, right? If we remember, let's say the last 10 iterations of our model, or on this axis, maybe the last 100, and we see that the validation loss is going down and then is bottoming out and then it's starting to come back up. Well, then we could like go back a few steps to where we thought it was a minimum, and we say like this is our model. We're just gonna like stop there, right? So that's just early stopping. But we can also put constraints on the model. So one popular one is L1. And that's basically where we take all the parameters in the model and we take their absolute value and we add them together. And then we're just going to add that to the loss function with some constant. Okay, and that'll be L1. L2 is kind of the same thing, but we're going to take the square of all the parameters, and then we're going to add that to our loss function. We can take a little bit of L1 and L2 together, so we can have two constants, and we can put them both in, and that has some really nice properties. And there's many other techniques that will help regularize the data. In fact, doing stochastic gradient descent in and of itself regularizes the data. And we talked earlier about batch norm. That actually ends up regularizing the data. And so like a lot of things we do help to regularize data. One thing that prevents the model to some extent from memorizing the training input is dropout. And so with dropout, we can add dropout after any of the layers in our model. And then while we're training, it will just ignore like some percent of the neurons. So it might ignore like 10% or 20%, like a good fraction of the neurons in any particular batch. Okay. And that really helps it helps prevent it from memorizing specific answers and overfitting. Okay, so if we're going to put in these regularizers, we're putting in a lot of additional hyperparameters in our model. So, like how much L1, how much L2 are we putting in, how much dropout. These are all new parameters that we have to optimize over. And so that's where cross-validation becomes really useful. And so, I've shown you, well, I can, divide my data set into a training set and a test set. But I can also take that training set and I can divide it up, and I can kind of optimize all the different hyperparameters in my model, like leaving different validation sets out. And so I can use all of my data to fit those hyperparameters instead of just 20% of it. Skip that. Okay. So here's an example of what would happen as we start to overfit the model, right? And here you can see it's the orange points are the data points that I generated. I generated them from a simple model, just a single line. And you can see here we're getting like fairly poor behavior. The loss is going to be really low because the model is like, predicting most of those orange points exactly. In fact, I think this model may be fitting all of the orange points exactly. And I think the orange is just like in front of the blue, so you can't see it. But regardless, the things that the model is doing, interpolating between those orange points is kind of nonsense, right? And certainly everything it's doing extrapolating from that line is, complete nonsense. Okay. So we can take the same model and we can run it with early stopping. And when we do that, we get the following curve, which looks pretty good. Like it's not quite linear on the edges, but the rest of it looks pretty good. Like that's a pretty good answer, and it's only getting weird in the extrapolation range. And honestly, like if you looked at that data and you didn't know that it was generated from a linear model, you might think that it's got a little curve in there. It almost looks like quadratic. We can overfit our model and then add an L1 term, okay? And this is kind of what we get if we put some L1 in, and now we can, overfit the model as much as we want. And here's our output. So it's still doing pretty good. It's doing bad in the extrapolation range, but it's doing pretty good over most of the range of our model. And on the left, what I'm showing you is I'm showing you the value of all the parameters in the model, right? So you can see what L1 is doing. L1 is driving almost all the parameters in our model to 0, right? And then you can count, the total number looks like 10. There's 10 non-zero parameters, and those are kind of driving the whole model. And if you were to look at the line, you can probably see like 10 different like segments there or something. Okay. What about L2? Well, if we look, like that's a pretty similar fit, but what it's doing with those parameters is very different, right? And so if we think about it this way, if we have multiple parameters in our model that are all saying the same thing, L1 is going to want to it's going to pick the best one, the one that is just infinitesimally better on like one data point in our set than the others. And it's going to like over optimize the loss based on like whichever parameter actually fits the data the best. Okay, so it's going to pick the 10 best, or however many best parameters, and it's going to drive everything else to 0. L2 is driving it to 0, right? Because we're putting a penalty. The loss function is going to include the sum of all those parameters, so it wants them to be small. With L2, we're going to square those parameters. So if we have two parameters that maybe one is infinitesimally better than the other one, if we want to put the full weight of the slightly better parameter into the model, let's say that's the weight is like 0.1, right? So we're going to put the full 0.1 in, and we're going to drive the other parameter down to 0. And so now our L2 is going to be 0.1 squared or 0.01. But now what if we take 0.05 of this parameter and 0.05 of that parameter, right? And now because it's squared, like we're actually the L2 penalty is much less, right? Because now I'm taking half of those numbers and then squaring it. So I, I get a fourth and a fourth, I add them together, I get a half, right? So, if we have two parameters that are equal, my L2 is only going to be 1/2 as large if I split it between them, as opposed to making, one 0 and the other one full value. And so you can kind of see that, right? Like, look at all these parameters in the middle here that are essentially like the same value. It's like it's creating a model, and you can almost see, like, there's a parameter here, there's a parameter here, there's a parameter here, there's one here, there's one here. There's all these parameters in my model that are like, they're about the same. And I'm splitting the L2 over all of them, right? Okay. And so, produces something similar, but it, makes us pay attention to more of our points. So it's a little more popular than L1, and L1 plus L2 has some nice properties as well. Okay. Now, so L2 is probably like the most popular, one of the most popular ways to just add some regularization to our loss function. In general, we don't just add we could add the L2 term if we were computing the gradient ourselves, like we did in the, in the first example that we wrote out, where, P equals P minus learning rate times gradient. If we're doing our update that way, it's kind of okay if we just add L2 to our loss function. But in general, because Adam and a lot of these terms that use momentum are storing like what the gradient was in the prior term. If we add our L2 to the loss function, then compute the gradient of that, then that gradient is getting amplified every step that that we do an update. And so it builds up a momentum in a certain direction, and the amount of momentum it builds up depends on how big that parameter was when it was initialized, and it just like it kind of wreaks havoc with things, and it's not good. And it sort of dilutes out and sort of randomizes the regularization effect of the L2. And so in practice, we're probably going to use an optimizer like Adam, and then sometimes it's called Adam W, sometimes it's just called Adam, and there's a parameter for weight decay. But we basically compute the gradient first, and then after we've computed the gradient, so we don't put the L2 in the loss function. After we've computed the gradient, we add the L2 term in, as part of the optimizer in the parameter update, but we don't include it in the gradient, so it doesn't like have momentum and keep pushing us in that direction. Okay. So in general, when you guys are like building models, you can just use some of these existing optimizers like Adam. You can put in, like weight decay equals like whatever, and it'll take care of all this stuff for you. Yeah. Okay. Dropout, I think, is kind of interesting too. So here's what overfitting that same model looks like with dropout, and here you can kind of see it's not really as linear as the other ones, and it's still doing weird stuff at the end, but it's got a kind of a nice like smoothing effect in the middle. And we get that just by dropping out 50% of the neurons like every time we run it, and it kind of makes everything like a little redundant. This is on the left, you can see what the parameters look like. I don't have an intuitive explanation for like what that cloud means. I just thought I would like also show it. I'm sure there is like a good way to understand that. And adding dropout is pretty easy. We just put in a dropout layer, and then we can specify like what fraction of nodes to drop out, like in that layer, and we just stick that into our model. Okay, batch normalization is another way to regularize things, and also help the back propagation algorithm, you know, distribute gradients from all the way from the loss function to earlier in the model. And one of the problems there is as we go layer to layer to layer, some of those gradients can disappear, and so or explode. And so batch normalization helps that by saying for each activation in our model, we're gonna set the mean and the standard deviation to 0 and 1 respectively, for all of the examples in a particular batch. Okay, that's kind of how that works. This ends up working really well, and it allows us to train like much bigger models. This was the original paper, batch normalization, accelerating training by reducing internal covariate shift. So the idea there was, you know, I used to have, I used to be getting input from these other layers that, you know, that had some set of weights, and in my parameter updates, like those other layers and the inputs coming in have shifted. And so now like I also need to like shift this layer because it's on like it's on a moving landscape. There was a nice paper, well, I guess I don't have it. A nice paper that came out of a group here at MIT that actually showed that's not true. That's not what batch normalization does. But empirically, we know batch normalization works, and so the new hypothesis on how it works is that it actually smooths out the loss landscape. So if the loss landscape is like kind of bumpy, it smooths it out. So you get not as easy to get stuck in local minima. I don't think I want to get too far into. Oh yeah, here's a paper from MIT, kind of showing how it works. And I think that's all I want to say, kind of about some of the theory and some of the algorithms behind training these networks. So let's go back and let's see how our model did. Is this from this run? Okay. Yeah, I think this is from here. So we started out with our first epoch, and we got up to 86% accurate, so better than 75%. That's great. And here I'm looking at my test accuracy, so I'm only looking at so you can see the loss here. Let's go back. My loss started out after the first epoch at 0.38. Okay, so that's the function I'm trying to minimize. And that's my loss on my training data, right? So that should just like generally be just be going down each epoch. But my test accuracy, this is on the data I held out, right? So this is my loss on the training data, is my accuracy on the test data. So definitely my loss is going down. That's to be expected. But what's nice is my test accuracy is generally going up. So here we're kind of in the we were in the 90s. We're hovering around 90, and if we get let's go all the way down, our loss is getting pretty small. And our test accuracy is about 90%. So pretty good, better than random. I thought it was like 99.9 because I had the wrong training set. But it means there's more to learn here. So what else could we do? Well, we could start with a more sophisticated model. We just had like a really simple neural net with 3 layers. So, you know, we could put different kinds of layers or more layers in there, or we could actually start with a different way to represent those molecules, like a graph neural net or something like that. And that's probably, if I had to guess, that's probably where we could gain some ground is having a more sophisticated embedding that was going into our model. But here we kind of see how all the features work. And let me just let's plot this out. Let's see what our loss function looks like. And so we can see it starts out pretty high, and then as time goes on, it really starts to decrease here. And you know, our loss gets pretty low, and sometimes it spikes, right? And the same is true of our accuracy. And part of the reason for this is when we're fitting our model, we're not just trying to get the right answer, right? So if it crosses the blood-brain barrier and it's a 1, we're not just trying to get a probability greater than 0.5. Our model is getting maximum or minimum loss if it's predicting with 100% confidence that it crosses the blood-brain barrier. And you know, if it doesn't, it's getting like it's you know, maxing or minimizing the loss by, you know, predicting 100% confident that it doesn't, right? And so even if the model is perfectly accurate, the loss is not necessarily 0 unless the model is 100% confident of the answer. And so that's really where like a lot of the overfitting comes in, is your model is getting trained and it's getting rewarded for being like overly confident about you know, test answers that it's memorized, rather than you know, just trying to generalize based on what it's seen. Okay. And that also explains a lot of the, you know, why your loss can go down and your accuracy can go up, or vice versa. Okay, so that's all I have to say on that, and that is the end of the small molecule section. Professor Kellis is going to talk to us about a few more topics. I think GWAS and some other exciting areas of deep learning and life science for the next 2 lectures, and then on to the final module. All right.